Hi guys, Albert here again for my channel Einbert Electric. Today I will discuss about voltage drop calculation. This is for single phase and three phase circuits. What is a voltage drop? A voltage drop is the decrease in electrical potential along the path of current flowing in an electrical circuit. This drop starts from the point being considered a power source point to the point of load connection. So voltage drop means, or voltage drop exists if there is a current flow through a conductor and that conductor has a resistance or impedance. As we remember in our Ohm's law, V is equals to IR. If there is a current flow and it is flowing through a conductor with a resistance, it will have a drop, or it will have a voltage drop. So why we calculate voltage drop? Number one, this is a code recommendation. As we will see later, I will show you uh, why the code recommends this. Number two, ensure efficient operation. This is also mentioned by the code. And number three, in many places in the world and in your local places, this is usually a requirement in electrical design. And to make it in detail and in general, voltage drop actually affects conductor sizing. Now let's go to the code recommendation. It is found in this section of the National Electrical Code, branch circuit ratings, 210.19, conductors, minimum capacity and size. A. Branch circuits not more than 600 volts. And mentioned in informational note. This is number 1, informational note number 2, informational note number 3, and here it is mentioned in informational note number 4. Conductors for branch circuit as defined in Article 100, size to prevent a voltage drop exceeding 3% at the farthest outlet of power, heating, and lighting loads or combination of such loads, and where the maximum total voltage drop on both feeders and branch circuits to the farthest outlet does not exceed 5%. Provide reasonable efficiency of operation. So the reason is to provide reasonable efficiency of operation. Why? Because you remember in our basic, like lighting, if the voltage, for example, a lamp, it has a rated voltage of the 220, and then you will supply a voltage of, for example, 200. It is basic there. It was taught us that if we decrease the voltage of the lamp, it will affect its life expectancy. So that's why, that is one example why this code is telling it will provide reasonable efficiency of operation. And of course, if you are putting a low voltage to a lamp with a higher rated voltage, you will see that later when you decrease more the voltage, it will just flicker. It will not give the correct or expected output. Okay, so informational note number 4, it clearly explains that for the branch circuit from the source of the branch circuit from the branch circuit overcurrent device to the load. You have to limit your voltage drop to 3%. And for the feeder, from the source of your feeder to the end point of your feeder, you have to limit it into 2%. And for a total of 5% from the source of the feeder to the end of your feeder, which is the start of your branch circuit, and going to the end of your branch circuit, we have to limit the voltage drop to 5%. This is what the code recommends. Now let's see the single phase voltage drop formula. This is the general formula to calculate for voltage drop in volts. It is equals to 2.0 times K times IFL times L all over the circular mill. What this means? So K is the resistance constant per conductor, that is 1 circular mill in diameter and 1 foot long at an operating temperature of 75 degrees centigrade. K for copper is 12.9 and K for aluminum is 21.2. Number 2 here is the single phase constant. So take note, if it is a single phase, your constant is 2. And L obviously is the length of the circuit from power supply to the load in feet. So we are using here the English units. IFL, full load current in amperes. Okay, and VD is the voltage drop. CM or C mil is the conductor cross-sectional area in circular mills. And also, this is the three-phase voltage drop formula. As you can see, it is almost similar formula except this factor of 1.732. So it is the same except the three-phase constant of 1.732. This is for three-phase. So the same formula for the single phase, your factor is 2. For three-phase, your factor is 1.732. Now, there is a table in the NEC which is called Conductor Properties. This is table 8, Conductor Properties. This is the table. So we can see here some columns like size of wire, area and circular mills, conductors, and DC current resistance. So how are we going to use this table? So in this portion of the table, which is the size and area in circular mills, this size is the size of conductor, and the area here is the cross-sectional area of the conductor here. Okay, now let's go to the voltage drop calculations. Remember guys, in my video lecture number 4, which is the single motor complete design calculations, we arrive in these results. We have the breaker here, then conductor size, then the isolator or disconnecting means, then controller, overload relay, and of course this is the motor load. So there we have calculated the conductor. The final conductor is 3 by number 4 or 22 mm squared with 85 ampere capacity, THW or THHN conductor. So here let us see if this conductor size, what will happen. This conductor was not greater than 30 meters. So we assume that during that calculation that the distance run of this conductor is less than or equal to 30 meters only, or 100 feet. Now, using the three-phase formula, because that motor we calculated was a three-phase motor, so we will use the three-phase formula. So to calculate, we use 1.732 for three-phase factor, then 12.29 for copper conductor, and remember that current which is taken from the table is 66 ampere, and we use 98.4 feet, which is equal to 30 meters. So here we limit the length of the conductor to 30 meters. And also, this 41,740 circular mils is the cross-sectional area of the number 4 or 22 mm squared conductor. Let us see. So we have a voltage drop of 3.5 volts as calculated, and a percent voltage drop of 0.88. As you can see, 0.88 is much lesser compared to 3%, which is the recommended by the code. So that means this conductor size is more than enough to carry the load current in a distance of 30 meters or 98.4 feet. So this 0.88 is less than 3%, and we limit it into 30 meters. Okay, and using the same conductor size, which is number 4, 22 mm squared. Okay, now let us see if we increase the length of the conductor from 98 feet to 350 feet. So let us see what will happen. We increase the length of the conductor. Now we get 12.36 volts, which is equal to 3.09%. So 3.09 means almost equal to the 3%. So what does this mean? So 350 feet, this is equal to 106.71 meter, and this circular mills 41,740 is the same conductor, number 4 mechanical gauge or 22 mm squared, and we get 3.09, or we can say almost 3%. Now let us see, we increase more the length of the conductor into 600 feet. So what we get, voltage drop is 21.2 volts, and how many percent? Now it comes out to be 5.3%. So what does this mean? So by increasing the length of the conductor into 600 feet, which is almost 183 meters, and using the same conductor size, number 4, 22 mm squared, we get 5.3%, which is greater than 3%. So now, although this is a recommendation only by the code, it looks like we are not following the recommendation. So if it is greater than 3%, what we will do? So what we will do to decrease the voltage drop? Of course, we have the basic that if the conductor is smaller, and in a particular length there is a resistance, right? Now compare it to the another size of conductor with the same length. Now which one will have more resistance, the smaller conductor or the bigger conductor? Of course, it is the smaller conductor which will have the higher resistance. So here in the voltage drop calculation, we have to increase the size of your conductor to reduce the resistance. Of course, when you reduce the resistance, the current is the same, so your voltage drop follows that it will also reduce. Okay? Now here, we will see what size of conductor is exactly required. If we maintain this 600 feet, that distance we will maintain and we will limit the 3% voltage drop. So here 600 feet, we will maintain the 600 feet because in actual installation, if the distance is 600 feet, you cannot decrease your cable or conductor length. It will be that length only. So we will also fix the 3% in this formula, and we will try to get the area, the cross-sectional area, which will determine the size of the conductor. So applying the formula, now we put circular mill on the left side. What we will get is we have 73,731.24 circular mills. So what does this mean? How are we going to uh, determine the size of the conductor? From the table of that table which I've shown, properties of conductors, at least 73,731.24 circular mills is required. So we have to look for a circular mills which is greater than this. If we have exactly the same or greater than this, so there the next one is lower than this, so we cannot use that one. We have to use the greater than 73,731, and this corresponds to number 1 American wide gauge, which is equivalent to 38 mm squared, having 83,690 circular mills. This means that if the cable or wire run is 600 feet, the conductor must be sized up to number 1 or 38 mm squared to be able to comply with the 3% voltage drop recommended by the code. Okay, it is clear. Now, see here in the conductor properties, this is number 4 is 41,740. This is the size of the conductor. 4 American wide gauge, 22 mm squared. Now we increased it into 38 mm squared or number 1 American wide gauge. See here, the circular mills 83,000. The next lower one is 66,000, which is far less than 73,000. So we cannot use that. We have to use the higher value. Okay. Now, as a final summary, let us again overview that motor branch circuit. We have the breaker, conductor size, equipment ground conductor, isolator, disconnecting means, controller, and the motor nameplate. See here, initially we have 22 mm squared or number 4. This is during the time the length of the conductor considered is only less than 30 meters, equal or less than 30 meters. Now we increased it into 600 feet or 182.93 meters. So from 22 mm squared, we increased the conductor size into number 1 American migrates or 38 mm squared due to voltage drop. We limit it to 3% because we increased the length. And this 130 ampacity of the new size of the conductor, note that we cannot use this ampacity. Why? Because this purpose was to uh, negate the voltage drop. This is not used for current ampacity. We still have to use the 85 ampere ampacity.